morning.
Morning, sir.
How are you guys? So in today's lesson we have about 15 minutes, right? So that's little time to cover the topic. So we're going to focus on the electrostatics, right? So last year we did electrostatics, the introduction of electrostatics, right? We talked about a charged object and neutral objects, right?
Yes.
So now, from you guys, what is the difference between a charged object and a neutral object? Yes?
Charged has a positive sign. Yes.
You can say that? Yes? Anyone else? No. So in order for an object to be charged, we should have what? An imbalance between charges, right? Remember we have positive and negative charges, right?
Yes.
When you have an object that has an equal amount of a negative and a positive charge, it is neutral, right?
Yes.
When we have an imbalance of those charges, we have what? A charged object. So when you have more electrons, you have what? A negatively charged object. When you have more protons, you have
Positively charged.
negatively charged object, right?
Yes.
So now in grade 11, we introduce what? An interaction between the two objects, right? We need to know what happens when two or more charged objects come to each other, or rather when they interact, right?
Yes.
So, anyway, so you may have experienced a shock when you touch someone. Why is that the case?
Because of the charge.
Because of the?
There's a charge on me or them, so it's unbalanced.
There's a build-up of charge in one of you guys. Same thing as lightning, right? There is a build-up of charge in the clouds. So the lightning is a result of what? Of the electrical discharge, right? So that feeling that you get, that shock, it's because of what you are discharging. Hence, this, you think you're bored, right? So now today, as specified, we're going to be focusing on one, the behavior of two or more charged particles, right?
Yes.
Remember, a particle can be charged when it's positive or negative, right? So how do they behave? We look at Newton's law of electrostatics, right? We have Fe, which is what? The electrostatic force that the two charges exert on each other, right?
Yes.
So let me just do this. So we have the electrostatic force, which is Fe, right? We have Ke, which is Coulomb's constant. So you have units for electrostatic force, you have what? The Newton, and then for Coulomb's constant, you have Newton meters squared per Coulomb squared, right? This is a constant value. Whenever you use that value, it's 9 times 10 to the 9, right? And then you have Q1 and Q2. Q1 and Q2 are the charges that the objects have, right? Whether it's positive or negative. And then you have R. R is the distance between the two charges, right?
Yes.
So now, if you look at this equation, you can see that the electrostatic force is inversely or directly proportional to the magnitude or the product of the magnitude of the two charges. So the greater the charge, the greater the
Electricity force.
right? It is also inversely proportional to what?
The distance.
The distance squared between the
Two charges.
So now when we say inversely proportional, if they are further apart, do we experience a greater or less electricity force? Less, right? When they come closer together, a stronger or a force, right? So this, from these two definitions, we can come up with what? With the definition from this one. It says what? The magnitude, or rather the electrostatic force that two charged particles exert on each other is directly proportional to what? The magnitude of their charges, and inversely proportional to the square distance between them. Right?
Yes.
So when you bring them closer together, greater electrostatic force. When you separate them, less. Any questions so far?
No, sir.
Alright. So now we come to a concept of like and unlike charges. I think you still remember this.
Yes.
What do like charges do?
Attract each other.
They repel each other. A boy and a boy will never. I will never be attracted to another we are like charges, right?
Unless you are gay.
Wait, unless, but in this case, we are dealing with the fundamental laws of the universe, right?
Yes.
So in this case, if like charges, like me, I'll never be attracted to that guy if he holds. Right? We are like charges. But now, unlike charges, a girl and a boy, right? I can be attracted to you. Who knows, maybe I am. But anyway. But anyway, yeah. Quiet, please. So unlike charges do what? They attract each other. Like charges, they repel each other. Any question?
No.
Are you sure?
Yes. So I have a question.
Please ask.
So unlike charges like positive and negative.
Yes. Positive and negative and like. Positive and positive like. Negative
Oh,
and negative
okay.
like. Right?
Positive, like.
Like.
Negative, positive,
And like.
Oh, thank you, sir. I have clarity now.
So like's the same. Positive.
Like is the same, yes. When you have a negative and a negative charge, don't always move away from
Each other.
sharp.
Yes.
And then now let's consider these two charged particles, x and y, at a given distance 0,4, right? So from here, we can find what the electrostatic force that these two objects exert on each other. Now remember our equation. Our equation is given by what? Fe equals to Ke multiplied by Q1, Q2 over R squared, right? You do not need to include the signs, right? The signs are just there to give you direction, right? So when you substitute there, you just substitute what the magnitude. Remember that force is a vector quantity. So you have to specify what your direction. So in this case, if I were to say to you, find the force that y exerts on x. Yes?
So in a test, you'd have to put the positive and a negative because you said we have to show something.
When you substitute, when you're calculating the equation, there is no need to do that. Because the signs are just there to tell you the direction, right? Because in this case, I know that x will be attracted to y. So the direction of x is towards particle y. The direction of y will be towards x. Remember, a vector has to have both magnitude and direction, right? So those signs, you don't need to substitute them in the equation. They are just there to tell you what the direction, right? Any questions?
No, sir.
All right. So now, let's do this. What do you think I should do? I substitute as they are, right? So I have Fe equals to, what's my constant value?
9 times 10 to the power 9.
9 times 10 to the 9. What's my charge number 1?
10 times 10 to the power
10 times 10. So someone here could just say 10 squared, right? So this is divided by what?
0.04.
0.04. Another thing to consider, the unit is.
Let's say it says it's microcoulomb, not coulomb.
Yes, thank you very much.
So
That's what I wanted to say, what you should consider, right? You have what your centi, they can give you in centicoulombs, microcoulombs, nanocoulombs. We know that the microcoulomb is times 10 to the minus 6, right? So in this equation, this can be written as what? Times 10 to the minus 6. I can write it as squared because it's 10 and 10. Again, what are the units of the distance between the two charges? It's always in meters, right? So they give you in kilometers and centimeters. You always have to convert back to
Meters.
right?
So it always the ratio, the R is always meters,
It's always in meters.
and then the one on top is always nano.
It's always in coulombs. It's always in coulombs. Because remember, you are giving this as 10 microcoulombs.
So we have to make it cool, and it's giving to us
In microcoulombs.
Yes,
So it's 10 times 10 to the minus 6 coulombs. So it always have to be in coulombs, yes?
That one, 9 multiplied by 10 to the power 9
It's
is
nano.
10 to the power minus 9.
It's nanocoulombs. Times 10 to the minus 9 is nanocoulombs, right? So either way, if they give you a distance not in meters, you always have to convert it back to meters. If they give you a charge that is not in coulombs, you have to convert it back to coulombs. Sharp. So in this case, you can just punch this into your calculator. What do you get? Fe is equal to Yes.
I think your question is based on the constant.
Constant.
Is the constant minus 9 or just 9? That's
9.
Okay. Yeah, it's just 9. It's
Yes.
not a minus 9
Yes.
or anything.
Right?
Yeah.
Any calculators? Calculate for me. No calculators. Here's a calculator. Come on, guys. It's 15 minutes. I still have to go and talk about the electric field. Electric field strength.
Not state that we should give the direction.
You should. A force is always a vector.
Okay.
A force is never a scalar. The only thing a study scalar is your mass, time, right?
Yeah.
But your velocity, acceleration, force, momentum, displacement, those are your vectors. You should always specify directions. Sharp.
Yes.
State the force. Okay, anyway, the question did come, right? So, thus, state the force that X experiences due to Y.
So it's in opposite direction.
Right? So, remember Newton's third law. What does it say?
If you put an object,
Force will equal and opposite. Yeah.
If object A applies a force on object B,
No,
object
object
B
B is the same.
amount of force, but
In the opposite direction.
So the force that these two charges experience are the same but in opposite direction. So in this case now they say state the force that X experiences due to Y. So X is going towards, so we would say 5,63 times 10 to the minus 16 towards Y. You get it?
yes. But
No question. Yes, Thomas.
so what happens if maybe before I start answering the question, then I say my directions, maybe I'll say X
Towards
is
each
on
other.
the right.
You can say they are towards each
No,
other.
yes, but then if I say X is on the left and then Y is on the right, then
Yeah, we
and
saw
then
that.
I say that to answer question 2, I say that the answer is 5.60 times to the power negative 16 to the right.
Yeah, you can, but most of you not, right? You
Yeah.
have to put,
Oh,
you
the
know,
camp has
yeah, so
been-
that I see when I'm marking, right?
Oh, okay.
If you don't, you can just say towards.
Oh,
You're
okay.
giving me direction.
Oh, okay.
Sharp.
It is.
Now, if Y is fixed, right, but X is free to move, will the acceleration experienced by X be constant?
If Y is
Think of Newton's second law now.
okay, if Y is fixed,
Think of Newton's second law.
it's free to move.
Inertia.
Newton's second law says that an object will accelerate in the direction of the applied force, right? So in this case, remember, we just said that when they come closer together, the force increases, right? So when F increases, what happens to the acceleration? It also increases, right? So as Y comes closer to X, the electrostatic force that they experience will also increase. Therefore, the acceleration will never be constant. It will also change because the force is changing. Sharp. So in this case, no, because the electrostatic force will increase as the distance between the two charges decreases. Sharp.
Yes.
Okay, explain. Yeah, just
Just
explain.
explain.
This is the explanation. Yeah. So now what we're supposed to do, Mara, because the time is over, right? Because my lesson plan says I should cover also electrostatics, right? I'll just brush through.
Next period.
So, no next period, afternoon class. This is the afternoon class. So anyway, in this case, we have what? We have the electric fields, right? What is an electric field?
It's an area where electronic energy resides. I don't know if that's the right name.
No, but yeah, now something here. A region of space, right? Where another charged object will experience an electrostatic force, right? For example, let's say this is our region, right? So this is our radius of the electrostatic, or rather the electric field. If I place a charged object here, it won't experience what? An electrostatic force, right? The moment it moves in this space of region, it will do what? It will experience an electrostatic force. So electric field is what? It's a region of space where another charged object will experience what? An electrostatic force. Questions?